So I do my work with the North American Nanohertz Observatory for Gravitational Waves and the International Pulsar Time Array. And I promise you that by the end of the talk, those mouthfuls will make some sense. Okay, so this is the view of the universe that you would get if you looked outside for the last many thousands of years. You have in the center of the Milky Way, you have stars, you can see bright patches along the Milky Way. Milky Way is our home galaxy, and you see dark patches. This is the universe in optical light, one very, very narrow portion of the electromagnetic spectrum. If our eyes were sensitive to radio waves, radio is another frequency of the electromagnetic spectrum, this is what the sky would look like. You can see that there's all sorts of little fuzzy stuff going on, and there are all these little dots. These dots are not stars, but are objects known as quasars, which are jets emanating from supermassive black holes billions of light years away. A good fraction of the total size of the universe away from us. And they are so bright in the radio that we can see them here on Earth. If you take a look at the Milky Way, again our home galaxy, in different wavelengths of light, this is the view that you get. Starting at the top, if you look in the radio, you can see different emission from different features of things in our galaxy. Work your way down, you can see what atomic hydrogen looks like, molecular hydrogen, look down into the infrared, back down into the optical, and then X-ray, gamma ray. The universe looks very different in different wavelengths of light. And only in the last 100 years or so have we known this. For thousands of years, astronomers have been looking at optical. Within the last 100 years, we've built radio observatories. Now in space, we have X-ray observatories, gamma ray observatories. The entire electromagnetic spectrum is now up for grabs for research. And we are learning so much more than we could with just the very narrow band that optical light covers. Okay. What our project aims to do is detect not electromagnetic radiation, but gravitational radiation. Okay, so what does that mean? Einstein, in his general theory of relativity, said that masses and energies curve space-time. If this here is a grid of space-time with no mass in it, as soon as I add mass to it, all of space-time warps in towards that mass. This is the curvature of space-time. So that objects going around will no longer travel in a straight line, but will curve slightly around the object. And the larger the mass, the more extreme the curvature. Okay? So what are we trying to detect? Well, this past Monday, there was an exciting new result by the BICEP 2 team that claims that they have detected gravitational radiation, these ripples and curves in space-time, from the very early universe, from the very, very, very first fraction of a second of the universe. Our group, Nanograv and the IPTA, are trying to detect gravitational waves from supermassive black hole collisions. So in the last half, 2/3 of the universe, you have giant, massive galaxies, much like our own, at the center of which is a supermassive black hole, millions to billions of times the mass of our sun. The sun is over 300,000 times the mass of the Earth. At the center of which, when two galaxies collide, the black holes start merging in the center, and you get these really extreme ripples in the curvature of space-time. This is what we are trying to detect. We're trying to learn something about galaxy evolution models. We're trying to learn something about black hole dynamics from gravity, not from electromagnetic radiation. How do we do this? Well, we need a very, very, very extreme tool. This here is an object called a pulsar. It is the remnant of a moderate mass star. Once it explodes and goes supernova, leaves this object behind. It is approximately 10 kilometers in size, in radius, so about the size of Manhattan Island, a little over the mass of the sun. So take the mass of the sun, squeeze it into Manhattan Island, and you have this extremely dense object. Now this object rotates extremely quickly. It The slowest ones, one orbit is about a second. The fastest, most stable ones, which we use, are called millisecond pulsars. They have a period of about 1 millisecond. So you have this 10-kilometer ball rotating hundreds of times a second. Its rotation axis is different from this radiation beam. So if you imagine that I am now a pulsar, my rotation axis will be through my head. Have here my radiation beam. I have my two offset beams, and as I spin, I don't see anything, or you don't see anything, and then you will see a blip. A very, very, very accurate and precisely timed blip. This is one of the most stable clocks in the universe. These rival atomic clocks here on Earth. We can use these as our tools to detect gravitational waves. Okay, so how do we do this? Nanograv, so we observe the North American, so we have two telescopes in North America, a 100-meter telescope in Green Bank, West Virginia, so you have a football stadium-sized object that can rotate all the way around and observe the sky. Arecibo in Puerto Rico, a 300-meter telescope, so 3 times larger in diameter, looks up other parts of the sky. These are the two largest single-dish radio telescopes in the world. So our group uses these, so North America. We observe nanohertz frequency gravitational waves. That just means that you have these two supermassive black holes spinning with a period of 1 to 10 years. This is the range in which we're sensitive to. And we want to observe these pulsars, these clocks up in the sky. As light travels through space, it travels at a rate of approximately 1 foot per nanosecond. So in that step, it only took light 1 nanosecond to move across the stage. We can use these very precise clocks to then measure distances. How does that help us? If you have a gravitational wave passing between you at the Earth and a pulsar here, pulsar spinning, the separation between the Earth and the pulsar is changing ever so slightly. In fact, it is changing on the order of tens of meters over a distance of 1,000 light years. How big is a light year? The moon is 250,000 miles away, and it takes light about a second to reach there. The sun is 93 million miles away, and it takes light 8.5 minutes to get from there to us. So you can imagine that 1 light year is this incomprehensibly vast distance. Now you take us, the pulsar, 1,000 light years away. It's spinning around. The light is traveling towards us, and we are measuring tens of meters distance change because gravitational waves are causing space to expand and contract by ever so slightly. And so what we want to do is build a galaxy-wide observatory. We have our 2 telescopes down here on the Earth, and we have an entire array of pulsars in the sky. Why do we need an array? Well, if you have a pulsar here, and a pulsar here, and a pulsar here, as gravitational waves pass through, you can now start to tell where the gravitational waves are coming from. You can tell what galaxies have these supermassive black holes merging, and then you can link them to other astrophysical models about how the universe evolves. We expect to detect, with this method, gravitational waves of this frequency range in the next few years. And to do so, Nanograv is a part of the International Pulsar Timing Array, which is comprised of 2 other similar groups, one in Europe, one in Australia, so that we have full sky coverage. We each have our own arrays of pulsars in the sky, and we are working very hard developing new instrumentation, new methodology, so that we can really, very precisely click off the pulses from each of these pulsars. And as we do so, our knowledge of the distance between each pulsar improves. And so we hope that within the next 3 to 5 years or so, we can join the BICEP 2 team in ushering in this new era of gravitational wave astronomy. Thank you.